Okay, let's go ahead and start here. Okay. We'll talk about the exam a little bit before the end of class. Hope you're ready for it. You got a good one. Okay, so last time we finished up with IR spectroscopy. Today we're going to get into a new spectroscopy, which is NMR spectroscopy. Okay, NMR stands for nuclear magnetic resonance spectroscopy. So this kind of thing is, you get the same kind of thing if you go into the hospital and get an MRI. Just instead of saying they're doing an NMR on you, they said you're doing an MRI on you. It's the same radiation and so forth. Okay? It's relatively harmless. It just sounds worse than it is. Okay? So when you look at these three words here, does anything come to mind? Make you think of anything when you see any of those words? Okay, okay, you saw resonance, okay. That actually is not the same thing as what you've been doing with resonance structures. It's a different resonance, okay. Magnetic, so what does that tell you? Got some kind of magnetism involved, okay. We'll see that come out today. And what's that make you think of? What's that? Nuclears. What does that deal with? The nucleus. Okay? So something's going on with the nucleus in all of this here. Okay? So let's go ahead and take a look at the nucleus. Okay? Remember, the nucleus is the inner part of the atom. Okay, so let's suppose we drew that like that there, just a circle. Okay, do you remember what's inside the nucleus? Protons and neutrons. Very good. So let's draw those in here. Okay. What was the charge of the neutron? 0, neutral, and the proton. So what's the overall charge? Positive. Okay, so the nucleus is overall positively charged. Okay. Well, when you have a nucleus that can spin, okay, spin like a top, then it can do something here. When you have a charged particle that can spin, it can generate something called a magnetic moment that will represent with this arrow here. Okay, so if you've taken physics and you do the right hand rule, okay, however your hand is going, your thumb indicates the moment that's generated there. Okay, remember you might have done that with electric fields and things like that. Okay, here, when the nucleus is spinning, it generates a moment like that. So we can call this a nuclear magnetic moment. Okay, and this is crucial. It is critical to have this moment generated in order to do NMR spectroscopy. Okay, we'll see in a second. Okay, but it turns out that not all atoms from the periodic table can do this. Okay, so not all atoms in their nucleus have spin. Okay? In fact, a majority of those atoms don't have spin. Okay? But some of the few that are of interest to us, okay, are the hydrogen atom. It has spin. And so guess what? We can do NMR with hydrogen atoms. And C13, the isotope of carbon-12, has spin. Okay? Carbon-12 does not have spin. Okay? Carbon-12 is much more abundant than carbon-13, but it doesn't have spin. But at least carbon-13 has spin. So God's given us that. So we can be thankful. Okay? So these are the two main NMRs that are performed. There are some others, like fluorine and phosphorus, which get into more exotic things. If you want to take advanced spectroscopy, you can study those. But the two main that are used in every chemistry lab are hydrogen, or sometimes called proton NMR, and C13 NMR. Okay? So we'll often write those like this. Okay? And so those are the two we're going to look at. And those are to our advantage, aren't they? Because organic molecules have what? Tons of hydrogens in them. So we like that. And organic molecules have carbon in them. So we can look at those. Okay? But things like oxygen, those don't have spin, so we can't look at things like alcohols and that kind of thing. Okay? But at least the carbons and hydrogens do. So that's what we're going to focus on in this chapter, chapter 13 of the book. Okay? So with all this introduction here, let's come back and talk about the spin. Okay? This NMR, we covered IR last time in one lecture. NMR is going to take several lectures as it's a little bit more involved. Okay? So let's look at some spins here. Okay? And let's first of all start by looking at hydrogen NMR or proton NMR. Because if we can understand proton NMR, we're going to see we can very easily understand C13 NMR. So to begin with, let's say that we had a big collection of hydrogen atoms, something like that. Let's just pretend we pulled a bunch of hydrogen atoms off molecules and we had a collection like that. Okay? Remember that each hydrogen atom has its nucleus that can spin. And so each of those can generate a magnetic moment. So let's draw those. Okay? But we don't have to draw them straight up. They can be in a multitude of directions. Okay? So they can be at different angles or even down. Okay? So here, with a collection of hydrogens, we can have a variety of spins, okay? Or what we call sometimes a random array of spins, okay? Well, now what we're going to do is take these hydrogens and we're going to apply something here, okay? Anybody know what B stands for from physics?
Beta.
It stands for magnetic field. Okay. So we have a magnetic field that we're going to apply. So that's the M of NMR. So we're going to apply it in this direction here. And what that's going to do is have an effect on these individual magnetic moments. It's going to cause each of them to make a decision. It's going to cause the ones that are pointing up to some degree to go fully up, and the ones that are pointing down to some degree to go fully down. Okay? So let's go ahead and draw that. Okay, so we'll call that B applied. So the result of B applied is this kind of thing here. Okay? So we'll get a collection that are pointing down, and we'll get a collection that are pointing up. Okay? So you see what the magnetic field does. What does it do? It creates one of two spin states. Okay? In fact, it creates both spin states. Okay? This spin state here at the top, I want to shut that door. What direction are those spins going in?
Yeah.
Down. Okay? So maybe we can call these spin down. How's that for being creative? Okay? And what do you think we can call these? Spin up. Okay? So these are our spin states. And how are spin states formed? By applying the magnetic field. Okay? Well, we can also give these other names a little more technical. The spin up, sometimes called the alpha spins, and spin down, sometimes called the beta spins. Okay? So this is the critical thing that we find, and there turns out to be one other difference between these spin states. Okay? One difference is one goes up, the other goes down. What do you think the other difference might be? Okay. Might be an energy difference. Which one do you think would be of higher energy?
The ones on the opposite.
Okay. Spin downs, why do you think that would be higher energy? Okay. So it's fighting against the magnetic field. Okay? Anytime something's fighting or stressed, it's higher energy. Okay? Just like if you ever get in a fight, you have to exert some energy. Okay? So here, we can plot energy off to the side. So higher energy and lower energy spin states. Okay? So let's go ahead and redraw this a little bit. Let's redraw this whole diagram. Like this over here. Let's plot it as energy as a function of applied magnetic field. Okay? if we had zero magnetic field, all the spin states, remember, were random and so had the same energy. When we start applying the magnetic field, the spin states formed and they separated in energy. Okay? What is one thing you're seeing on this graph here? Anybody see something that's sticking out? What happens when you apply a larger magnetic field? You get more separation of spin states, don't you? Okay, so make sure you write that down. Okay, so the energy difference between the spin states increases with larger magnetic field. Okay, and that has an important result . When you get greater separation between spin states, you get better NMR resolution. Okay? That doesn't mean anything to you now, but it will a couple classes from now. Okay? So just tuck that away for right now. Okay? So better magnets give better NMR. Okay? Stronger magnets are better. Okay, weaker magnets, not as good. We have some really strong magnets downstairs by my office. They're 400 or 500 megahertz. Very powerful magnets that'll erase your credit card just like that. Okay? Schools that don't have as much money get smaller magnets, like 60 megahertz and so on. Okay? So, separation of spin states. Let's take this to the next step. Let's draw our energy diagram one more time like this. Let's just focus in on one alpha spin and one beta spin. Okay? So here we have a certain energy gap. Okay? What does that kind of remind you of? UV spectroscopy. Okay? Molecular orbitals. Okay? What happened in UV spectroscopy? What did we do? We applied UV energy, and what happened? The HOMO went up to the LUMO, right? Okay, we got a transition. We're going to do the same thing here, okay? But these are not HOMO and LUMO, okay? Here, what we're going to do is instead of applying UV energy, we're going to apply a radio frequency. Okay? Remember, frequency has the symbol nu here. Okay? And remember that energy is equal to h, Planck's constant, times the frequency. So this radio frequency will have energy to do what, do you think? To cause an alpha spin to go up to the beta spin. Okay? So we get a transition of alpha going to beta, so basically turning upside down. And that kind of transition is what we call a spin flip. A spin flip. Very important. Okay? This is what we do in NMR. The hydrogens feel the magnetic field, split into spin states, and then the radio frequency comes in, does a spin flip. When the hydrogen does a spin flip, guess what? The machine senses that, and it records a peak. Okay?
So does beta ever go to
Okay. Yeah, the beta, not due to radio frequency, sometimes it'll transition back down just on its own. Okay? But that's not important. The important thing is the other way in getting the spin flip. It'll relax back down there after you turn off the field and so on. Okay? So here we find how NMR generates a peak based on the spin flip. Okay? We also find another important fact that you can write it down, that every hydrogen type has its own particular spin flip. Every hydrogen type has its own particular spin flip energy. Okay? So every hydrogen out there will have a particular energy gap, and so will have its own what? Particular peak. And that's what we're going to develop. Okay? Any questions on that? That's where we are, just unpacking this theory a little bit. We'll see how it all comes together at the end. But every hydrogen type has its own particular spin flip energy, which generates its own particular peak. Okay? Before we go on, let me do some labeling here. Okay. This generation of spin states, when we apply a magnetic field, is what's called the Zeeman effect. Okay? So you see the Zeeman effect occurring what? More and more with higher magnetic fields. Okay? Just simply a guy named Zeeman found this out and got it named after him. Okay? So any questions on where we are now with these spin flips? So now do you see the importance of the atom having spin so that we can do that? Okay? We can't generate this setup here. We're not going to get any peaks, and the molecule's dead or the atom's dead to NMR. Okay, so let's go on to the next step here. And ask an important question. Okay. How do we get different hydrogens to have different spin flips? How do we get different hydrogens to have different spin flips? Okay? Well, let's look at two different nuclei here. Okay. So we have a hydrogen and a hydrogen nucleus. Does anything look different about it? I tried to draw on the same side. Okay. So I'm not getting paid to be an artist. Okay. So other than that, anything look different? No. So let's make a point of difference. All right. So being critical of my drawings. Okay, maybe that looks a little better. Okay. So let's have this one here. Let's surround it with this dotted line that we will represent as electron density. Okay. And we'll leave the one on the left alone. Okay. So let's take both of them and apply the magnetic field. Okay? And let's start asking some questions. Hopefully some easy questions. Okay. Which one of these two will feel the magnetic field easier?
No one on the left.
Okay. The one on the left or the one on the right? Okay. Why the one on the left? Okay. What are these electrons doing to this hydrogen? So what? Blocking it? Shielding it? Okay. That's the word we like to use, a shield. Do you have a shield? No? Well, you may not have a shield, but this hydrogen here has a shield. Okay? So we'll say that this is shielded. And what do you think we'll call the other one? Unshielded, or we'll call it de-shielded. Okay? So all hydrogens are shielded to some degree or de-shielded to some degree. Okay? We'll see how a little bit later. Okay? So over here, let's draw our NMR spectrum. Okay? This is the plot where our peaks are going to show up. And they're going to show up between the numbers of 0 to 15. And these numbers are called delta numbers, measured in parts per million. And we won't call them delta as much as we will call them chemical shifts. Okay? So whatever number a peak shows up on here, that is called its chemical shift value. Okay, so every peak will have a certain chemical shift value. Okay. Well, we need to designate the graph a little bit, give it some parameters. We say toward 0, that is where we have a higher magnetic field applied. And then down the other way is a lower magnetic field. Okay, so giving some parameters there. Okay, so low magnetic field is what we call down field. And what do you think we call high magnetic field? Up field. Where do you think shielded hydrogens are going to occur? More upfield or more downfield?
Downfield.
More shielded hydrogens. Okay. What do I have to do? And or I want this hydrogen to feel the magnetic field.
You have to increase the magnetic.
I need to have a higher magnetic field, don't I? So where are these going to occur? Upfield. Important. Okay? So shielded hydrogens occur more upfield. De-shielded hydrogens occur where? Downfield. Okay? Very important. Very important. Don't forget. Okay? You can remember it like DD, doomsday. Downfield, de-shielded. Okay? Any questions on this setup here? Okay? This is how you always want to look at an NMR spectrum, knowing what going toward 15 means and what going toward 0 means. Very important. Okay? Any questions?
I have a question.
Yeah.
I'm a little bit confused about the relationship between the chemical shift and the magnetic field.
Okay? Well, you just have to, just a fact, okay? So the smaller the chemical shift, that represents a higher V. Okay? That's just a fact. There's no logic there. Okay. Any other questions? Okay. All right. Well, you might ask, what makes a hydrogen shielded or de-shielded? Let's finish up class with that. Answer this important question. And let's answer this important question by looking at this molecule here. This is going to be our friend for the next couple of days. This little molecule is going to be our friend. What's the name of our friend? If you can't name that, you shouldn't be in the class. Chloroethane, or you can call it ethyl chloro. Okay? Well, chloroethane, it has two sets of hydrogens. It has these, and it has those. Okay? The CH3s are one group, and the CH2s are another group. Okay? And let's just give those letters. Okay? Let's maybe call these A, and those hydrogens B. Okay? Could have used any letters, but let's just label them. We want to start getting used to labeling hydrogens. Okay? Well, what extra atom is in there? That chlorine. What can you tell me about chlorine? Give me a fact about chlorine. Okay, yeah, it has 7 valence electrons, and yes, it is pretty electronegative. Okay, as it's right under fluorine, the most electronegative. So if it's electronegative, what does that mean that it's doing? It's pulling electrons. Very good. Okay? It's pulling electrons toward itself. Okay. Well, if that's the case, which set of hydrogens will be more shielded? A or B? Which will be more shielded?
B.
Okay, I'm hearing A and B. Can't be both. Well, let me ask it the other way. Which of those will be more de-shielded? A or B?
A.
Okay. So the chlorine is what? Pulling electrons away, and the A's can feel it better than the B's. Okay? So this chlorine is acting as a de-shielder. See that? So any electronegative atom is going to act as a de-shielder. So what? Is that the camera? Okay. So the closer I am to the de-shielder, what? The more downfield I will be. The closer I am to a de-shielder, the more downfield I will be. Good to see most of you writing that. Some of you are daydreaming. So which hydrogens will be closer to 15? A. And B will be closer to 0. Will be more upfield. Very important fact. We just covered that. I didn't draw the peaks. I just put an X where they show up. We'll see what the peaks look like later. Don't care about that now. But what we just covered is the important fact of peak position. One of the first things you want to do when you look at a molecule is determine peak position. And we just did that for our little friend. See how he's our friend? Okay. And we'll understand how to see what the peaks look like starting in next class. Any questions about peak position? Okay. All you have to do is identify your what? De-shielder, and then see which ones are closer to it. And we will start to see that there are other kinds of de-shielders besides electronegative atoms. We'll see, for example, double bonds can be de-shielders and other such things. Okay? All right. Well, let's stop here. I'll answer some questions for the exam.